All right, let's dive into a bit of a chemical mystery. We've got a showdown between two families of compounds that at first glance look almost identical, the alkanes and the alkenes. But, one of them is hiding a chemical secret that pretty much changes everything. So let's get right into it. So, picture this. You've got two beakers, both with a clear, colorless liquid inside. You're told one is an alkane, the other's an alkene. But how in the world do you tell them apart? Well, we're going to figure out exactly how to solve this puzzle with a really simple but brilliant chemical test. Okay, so before we can actually tell them apart, we've got to meet the families. See, both alkanes and alkenes, they're part of this huge group of compounds called hydrocarbons. The clue is right there in the name, hydrocarbon. You've got hydro for hydrogen and carbon for, well, carbon. So what does that mean? It means these are compounds made of only those two elements, nothing else. That's the foundation for both of our mystery liquids. And these hydrocarbon compounds, they're organized into families, which in chemistry we call a homologous series. Think of it kind of like a last name. Everyone in the family shares key traits, they react in similar ways, and they even follow a family formula. The alkanes, that's one family. The alkenes, they're another. And every family has its own code, right? In chemistry, we call that the general formula. It's the rule that every single member of the family has to follow. Okay, and right here, this is our first major clue. Just look at their family formulas. Alkanes follow the rule CnH2n plus 2, while alkenes follow CnH2n. The only difference is those two extra hydrogen atoms for the alkanes. I mean, it seems like such a tiny thing, but that little plus 2, it changes absolutely everything. And you can see this rule in action right here. So let's say we have two carbon atoms, right? The alkane version is ethane, C2H6, but the alkene, that's ethene, C2H4. See? Two fewer hydrogens. And it's the same deal if you have 6 carbons. Hexane is C6H14, but hexene is C6H12. That rule, it works every single time. So you gotta ask, where did those two missing hydrogens even go? Well, their absence points to the real difference between these families. It's not just about the numbers, it's about their entire structure. And this is the key that unlocks the whole mystery. So first up, the alkane family. We call them saturated. The best way to think about it is like a sponge that's just completely soaked. It can't hold any more water. Alkanes are full up with hydrogen atoms. Every carbon is bonded to as many other atoms as it possibly can, and they do it using only these really strong, stable, single bonds. But then you have the alkenes. They're the opposite. They're unsaturated. And why is that? Because at least 2 of their carbon atoms decided to form a double bond with each other. And that carbon-carbon double bond, that's the alkene family's secret weapon. It's their defining feature. So that double bond, that's what chemists call a functional group. And you can basically think of it as a little reactive hotspot on the molecule. The single bonds in an alkane, they're stable, they're kind of boring. But this double bond, it's the center of all the action. It's just waiting for something to react with. So that leads us to the big question, right? What does this reactive double bond actually let alkenes do that alkenes just can't? This special power is their unique chemical signature. Now, sure, both of them can burn. That's called complete combustion. But that doesn't really help us tell them apart, does it? The real secret, the one trick that only alkenes can pull off, is something called an addition reaction. And this is how we're going to solve our puzzle. An addition reaction, well, it's pretty much exactly what it sounds like. What happens is that the double bond in the alkane breaks open, and that allows a whole new molecule to just add on to those carbons. You start with 2 things, and you end with just one bigger thing. Simple as that. All right, let's watch this in action. So here's our ethene molecule, and it comes across a molecule of bromine. Then, bam, that reactive double bond opens up, and each of those carbon atoms grabs a bromine atom. And just like that, 2 molecules become one single bigger molecule called 1,2-dibromoethene. No mess, no leftover bits, just a clean addition. Okay. So now we have all the pieces of the puzzle. We know that alkenes have that reactive double bond. And we know that bond lets them do these cool addition reactions. And this unique chemical trick is exactly what we're going to use to finally tell our 2 clear liquids apart. All right, so here's the test. We'll take a sample of our alkane, let's use hexane, and a sample of our alkene, which we'll call hexene. And to both of them, we're going to add a few drops of something called bromine water. And you'll notice it has this very distinct orange-brown color. So, based on everything we've just talked about, what do you think is going to happen? I'll give you a hint. One of these test tubes is about to get a whole lot more interesting than the other. And here we go. The results are in. In the test tube with the alkane, absolutely nothing happens. The whole thing just stays that orange-brown color. Why? Because there are no double bonds for the bromine to react with. But look at the alkene tube. The orange-brown color, it's gone. It becomes completely colorless. And that's because those double bonds opened right up and gobbled up all the bromine in that addition reaction. And there you have it, mystery solved. That clear, visible color change from orange-brown to totally colorless, that is our definitive proof. The liquid that makes the bromine water go clear, that's our alkene. The one that stays orange, that's the alkane. Easy. So really, it all boils down to one simple, powerful rule. And here it is. Bromine water is decolorized by alkenes, but not by alkanes. That one sentence. That's the key to the whole chemical showdown. You know, this isn't just some neat little trick for the lab. This exact same type of addition reaction, it's the fundamental process that we use to create so many of the plastics and polymers that are all around us. It really makes you think, what other modern materials are built using this very same elegant piece of chemistry?